We will conclude this section with two more examples. So in example 5, we want to solve the differential equation x dy dx equals 1 over y cubed. So this is a separable equation because we can write this as follows. We can divide both sides by x and we see that we get dy dx equals 1 over x times 1 over y cubed. And so it's a function of x times a function of y. And then we can solve this by, we're going to start by multiplying both sides of the equation by dx. And then we get the following. We get dy equals 1 over x 1 over y cubed dx. And now we want to bring that 1 over y cubed to the other side because we have a dx here. And so we multiply both sides times y cubed. So we do y cubed on this side, and we multiply times y cubed here. And that gives us y cubed dy equals 1 over x dx. And then we'll integrate both sides. The antiderivative of y cubed, we're going to use a power rule. So that's going to be 1/4 y to the power 4 plus a constant of integration, but I'm going to save that for the other side. And then the antiderivative of x is ln of x plus a constant of integration. Now, if I want to solve that for y, I can first multiply both sides times 4. So if I multiply both sides times 4, then I get my y squared on the left, or y to the power 4, I'm sorry. And on the right, I get 4 times ln of x plus 4c, but I can give that a new name that's a constant as well, so that's k. So now I have y to the power 4 equals 4 times ln of x plus k. And I can solve that for y by taking the fourth root on both sides. So I get y equals, and then I get the fourth root of, and then ln of, I'm going to bring that 4 inside, so that will become to the fourth power. And since it's an even power, I don't have to worry about it being positive or negative. So I get ln of x to the power 4 plus k. And that's my final answer. And if I wanted to know what that value of k was, I would need an initial condition. Okay, so the next example, we're going to solve an initial value problem. And the initial value problem is dy dx equals x times y squared minus 1 over y. That's the same here. The only difference is we're going to look at two different initial values. So if we're going to solve that, again, this is separable, so we start by multiplying both sides by dx. And what we're left with, oops, and what we're left with is dy on the right, and on the left it's x over 1 times y squared minus 1 over y, and then we have our dx there. And so we want to get rid of this factor here, y squared minus 1 over y. We want that with the dy. And so we're going to multiply by the reciprocal of that fraction. So we're going to multiply by y squared. Oops, I need to flip that. So I'm going to multiply by y over y squared minus 1 on both sides. That will cancel out this. Now, two things that we have to note. First of all, y cannot be equal to 0 because then this term or this factor would be 0, and you would be multiplying both sides of the equation by 0, and that will result in a trivial equation 0 equals 0. So we cannot have that y equals 0. And furthermore, we cannot divide by 0. So y cannot be equal to 1 or negative 1. So y cannot be equal to plus or minus 1. Okay, now once we multiply both sides of that equation by y over y squared minus 1, we get on the left hand side y over y squared minus 1 dy, and on the right hand side we have x dx. And to solve, we're now going to integrate both sides, and on the left hand side we're going to need a substitution. So I'm going to use the substitution du equals y squared minus 1, and that gives us du dy equals 2y, derivative of y squared, and so du equals 2y dy, and let's solve that for dy. So we have dy here, and then we get 1 over 2y du equals dy. So that's the substitution that we're going to work with. Let's see. Use that over here, and our integral on the left becomes the integral of y over y squared minus 1. That's going to be u. And then our dy is going to be 1 over 2y du. And the nice thing what we can see there is that the y and the y cancel here. And so our left-hand side simplifies to 1 over u with a 1/2 in front du. That's a 1/2 that we can pull outside. And so on the right-hand side, we have 1/2 x squared plus c. So let's copy that down. Antiderivative of x is 1/2 x squared, and then a constant of integration. We could go ahead and multiply both sides by 2 here, and then we have the antiderivative of 1 over u du equals x squared, and then plus 2c, which I could call k. 1 over u, the antiderivative is ln of u, and that equals x squared plus, and at 2c, there's a constant of integration here, so that's going to change there, so that would be x squared plus k. And then u, remember, we chose u to be y squared minus 1. So when we're trying to figure out what this is, we get ln of u, and u is y squared minus 1, so we get ln of y squared minus 1 absolute value equals x squared plus k. Okay, at this point we can try to figure out what that constant of integration is by looking at the initial value. So we know that the initial value, the initial condition is y of 0 equals 2. So that means x equals 0, y equals 2. And when you plug that into that equation that we have right there, we then get that ln of the absolute value of 2 squared minus 1 equals 0 squared plus k. So we plug in 2 here, 0 here. And so on the left-hand side, we're left with ln of 3, and on the right-hand side, we have k. So ln of 3, that equals k. Okay, so our equation now becomes ln of y squared minus 1 absolute value is x squared plus ln of 3. We're going to exponentiate both sides with respect to e. So let's do that with purple. So I'm going to use e to this power, and then I'm also going to use e to that power. And the e and the ln, they cancel each other out. And so on the left, we have absolute value of y squared minus 1 equals, and there I have e to the power x squared times e to the power ln of 3. And what I'm using there is a property of exponents, right? So I'm using that e to the a plus b is e to the power a times e to the power b, right? And then e to the power ln of 3, that simplifies to just 3. So now I have the absolute value of y squared minus 1 is 3 times e to the power x squared. Okay, so now I know that y squared minus 1 is equal to plus or minus 3 times e to the power x squared because of the absolute value. But let's check in with the initial condition. I know that when x is 0, y is equal to 2. So if I plug in y equals 2, I get 4 minus 1, and that's 3, and that's not equal to negative 3. So I know this has to be the positive value. So I actually get that y squared minus 1 is equal to 3 times e to the power x squared. That's because this value plugged in here gives us positive 3. So it cannot be a negative. E to the power x squared is always going to be positive. So then I get y squared equals 1 plus 3 e to the power x squared. And then again, I need to take the square root, and then I have a choice, plus or minus. Since my y value is positive here, I cannot choose the negative is the incorrect choice. So I get that y equals square root of 1 plus 3 times e to the power x squared. That solves the first part of this question. Okay, now the next part, the only thing that changes is the fact that we have an initial condition y of 0 equals 1. And so we see from the initial condition that y equals 1, and we noted before that y should not be equal to plus or minus 1, so we can expect some issues there. But since this is the same differential equation, we get the same solution, the initial solution here. So I can actually take that solution right there and I can move it over here. And so I get ln of the absolute value of y squared minus 1 equals x squared plus k. Okay, and now we're going to use our initial condition. Our initial condition is that y of 0 equals 1. So that means x equals 0 and y equals 1. Now let's plug that into our solution. So we have ln of the absolute value of 1 squared minus 1 equals 0 squared plus k. So now that's a problem because on the left-hand side we get ln of 0, which is not defined. On the right hand we have k. So we cannot solve that equation that way. So what we're going to do here is we should already not even have tried that because this only worked if y was not equal to 0 and not equal to plus or minus 1. So when something like that happens, what you can try to do is see if the initial condition, the constant function that satisfies that initial condition, if that is a solution. So check to see if y of x is equal to 1. So the constant function is a solution to our initial value problem. So on the left hand side we have dy dx. So we get d dx of y, and y was our constant function 1, right? So on the left hand side we get that the derivative of a constant is 0. So that's our left side of our differential equation. And now on the other side we have to multiply x times y squared, which will be 1 minus 1, and then over 1. And you can see that that gives us 0 as well, right? 1 squared minus 1 gives us 0, and then we multiply that by x. So because these are equal, y of x equals 1 is indeed a solution.